So as we look at this picture here, okay, we see that hopefully at -2 we have a, what kind of discontinuity is that? Remember? Removable. And at 4, what do we have? Yeah, or infinite discontinuity. And then at 8, jump. All right. So they're all discontinuities, correct? We want to get a limit for how to determine if we have a discontinuity or not using limits. Okay, this is where we're headed. And also another piece. So right away, if we look, does the limit exist at 4? No. Does the limit exist at, the two-sided limit exist at 8? No. So I'm thinking if the limit doesn't exist, do you think it's going to be continuous? That seems like a pretty important piece, right? That there is a limit there. Okay, now, but over here at -2, we do have a limit, right? We have the limit as x approaches -2 of f of x, I guess that's what the function's called, is equal to some number. I don't know, I didn't put any numbers on the axis. But, you know, it would have the limit, right? This limit exists. So it must be more than just having a limit to make it continuous. Everybody agree with that? Because obviously that's called a removable discontinuity, which means it's not continuous. So, any ideas? Well, okay, how would we fix this discontinuity? We would, I heard fill in, we would put a point there, we would make it a closed circle. Right, so if I was going to take and put a point at, I guess we should give this a letter, right? We'll call this limit, we'll call that k. Just give it a name, right? So this limit is equal to k. Random constant, right? Just a variable. But we would need to put a point right here, correct? So mathematically, how do we say that we're putting a point at the ordered pair -2k? Well, to be continuous at x equals -2, we need the point -2k, correct? So for it to be continuous, we also need f of -2 to equal k. Okay, so what this is saying, and this is, I'll give you a nice definition of what it means to be continuous, but we need to have a limit, a defined limit, and you also have to have the value be the same at that function, right? Because if this was defined and it had a point up here, is it continuous? No, the only way it's going to be continuous is if we put a point right there at the point -2k. And to put a point, you just need to find the value of the function. So what we'll find is it has to have a limit, right, that's equal to some number. It has to have a value at that x value that matches the limit. It's kind of our definition. So it's really going to have 3 steps on how we define continuous. So what we saw here is that to be continuous, we need to have the limit, and we also have to have the value. So when doing this, I would recommend these 3 steps, kind of right, just think of them as 1, 2, 3. You need all 3 of these to be true to be continuous at a particular point. Okay, so if we're going to determine if a function is continuous at some value a, we need 3 things to happen. The first, there has to be a limit as x approaches a. And for our purposes, it's almost always going to need to be a 2-sided limit. There are cases, though, where the domain has endpoints, and if it's on an endpoint, you can just use a 1-sided limit because there's no other side. So for right now, just it has to have a 2-sided limit. F of a has to exist. So if you plug a into the function, you have to get an answer, right? If you plug a into the function and get undefined, it's not going to be continuous there. Or if you get indeterminate or, you know, whatever, that's not going to be a continuous point. And then that limit of f of x as x approaches a that we had in step 1 has to be the same as this value that we had in step 2. Okay, so it's got a limit, it's got a value, the limit equals the value. That's how we prove it's continuous. I would do that process every time. And you don't have to write a lot. You just say, you say the limit equals some number, you say f of a equals some number, you say this, and you're done. You don't need to write a paragraph. math usually suffices better than a paragraph. So if we go back to our picture here, we can see what happened with these three discontinuities. So if we look at -2, does the limit exist? Sure, there's a limit here, right? Is there a value here? No, so it failed step 2. It's not continuous. If we look at 4, is there a limit? No, failed step 1. If we look at 8, is there a limit? No. Oh, that was pretty boring, wasn't it? What if I put a point up here and we check -2 now? Still not continuous, but does it have a limit?
Yeah.
Does it have a value?
Yeah.
Are they the same? So it doesn't work. That's how we do continuity. So as an example of using our 3-step process for continuity, we have this piecewise function. Is f of x, we have x squared if x is less than -1, and then x minus 2 if x is greater than or equal to -1, is that continuous? Okay, so to do this, the first thing I do is I figure out is there a limit? Okay, so to do that, we're going to look at the left hand. Well, okay, there's a bigger question here. I made an assumption. Is x squared on its own a continuous function? It's a parabola. It's continuous, right? It's polynomial. Is x minus 2 continuous? Yes. So there's no potential for any problems with continuity except at -1, correct? Everywhere else we know it's continuous because it's a line and a parabola. They don't have discontinuities. So I'm going to need to go, and for our first step, I'm going to find the left-hand limit as x approaches -1 of f of x. Because if the left matches the right, then we know we have a two-sided limit. Okay. So if we're coming at this from the left, we're going to use this top equation, aren't we? Because we want to go where it's less than -1. That's the left. So we get -1 squared, which gives us 1. So let's do the right-hand limit. X approaches -1 from the right. So that would be the second part of the piecewise function. So here we would put -1 in here, and we would get -1 minus 2, which is -3. So does it have a limit? No. So what we would say here, if we were asked, is it continuous? We would say no. I mean, if it just asked, but we should probably say why. And that's because the limit as x approaches -1 of f of x does not exist. Right? Our first rule was that we had to have a limit. We don't have a limit, therefore it doesn't work. Okay, for our last example here, we have h of x is a piecewise function. There's 3 pieces. Now, the pieces themselves, the first part is a line. It should be continuous everywhere. X squared is a parabola. It should be continuous everywhere. This is a square root function, so it will have a domain restriction, but we know that if you put in anything bigger than -4 or larger, it works, correct? We get an output. It's continuous. So this one, if you think about that, the domain would be, for this function, would be -4 to infinity. It's continuous on the domain that it's listed. It's continuous between 0 and 5. So as it looks, all 3 pieces are continuous on their own, so we have to check where the pieces meet. It could be a jump discontinuity or all kinds, lots of stuff could happen. So to do this, the first place I'm going to check is at 0. So is h of x continuous at x equals 0? So we have to do 3 things, correct? Find the limit, find the value, find if they're the same. So to do this, to find the limit, I'll just label that number 1. The limit of h of x, notice I'm putting the function name in there, h of x, as x approaches 0 from the left. Well, left of 0 is defined by this top rule, correct? And then we'll do direct substitution. We'll get 0 plus 2, which would give us 2. Okay, the next thing we would do is the limit of h of x as x approaches 0 from the right. Well, to the right of 0 would be this second rule, correct? Which would give us the square root of 0 plus 4, which is also equal to 2. So, happy days. Well, it's kind of bittersweet, because if the limit exists, it means you got to do more work. Right? If it doesn't work, then you can just stop. So the limit exists at 0. So the second thing we want to do is find what is h of 0. Right? So we need to find if x is equal to 0, which rule do we use? So that's less than 0, but this is equal to 0. Now, you might have noticed it's going to be the same as the right-hand limit, because it's the same value. So we'll get h of 0 is going to be 2. So then our third step is that we can say that the limit of h of x as x approaches 0 is equal to h of 0. Right? The limit is equal to the value for step 3. Therefore, h of x is continuous at x equals 0. Right? By showing that. Right? It has the limit, it has a value, the limit equals the value. These were both equal to 2. Since 2 and 2, we're good to go there. Yes?
Do you have to do it for 5 as well?
Okay, now to finish this problem, we have to also check 5, right? Because 5 is a potential place we could have discontinuity. So we do know it's continuous at 0 and everywhere else, but we still need to check at 5. So we'll repeat the process. If I do let's see, for step 1, the limit as x approaches 5 from the left of h of x. So that would be our second equation, correct? That's the left of 5, immediately to the left of 5. So that would be the square root of 5 plus 4, which gives us 3. And then the limit of h of x as x approaches 5 from the right would be this bottom rule, right? Which 5 squared, that's feeling like 25. Okay, good news. The limit of h of x as x approaches 5 does not exist. So, h of x is discontinuous at x equals 5. Okay. Now, depending on how it fails can kind of tell you what type of discontinuity it is. Right? So here, since the two limits are different, it's looking like a jump discontinuity, right? If one of these would have been infinity, it would be an infinite discontinuity, right? If the limit exists but the value's different, as we saw on the graph, that tells us we're going to have a removable discontinuity.